Graphics in the media. Much like the graphs we learned from the previous section, there are other graphics in the media that we need to pay attention to and that we need to make sure we are aware of. But also we need to make sure that there are a few cautionary tips on reading graphics in the media because they sometimes can be quite deceptive. So let's go ahead and begin. Here's some definitions here that we need to know. First of all, we have something called a multiple bar graph that has two or more sets of bars that allow comparison between two or more data sets. All the data sets must have the same categories so they can be displayed on the same graph. I'll give you an example in just a moment. And in cases where the data is quantitative, a multiple line chart can often be a better choice. We also have a graph that's known as a stack plot, which helps also because it helps stack other data upon each other. And you can actually stack data in both a bar chart and a line chart. So for example, here's an example of a multiple bar chart or multiple bar graph. You'll notice that we have two bars per each degree here. So professional degree, doctoral degree, master's degree, and on down the line. And the dark red here is men and how much money they make on average. And then here the lighter color here are women and how much money they make. This can look slightly different with different types of graphs, but in a multiple bar graph, this is kind of what this looks like. We also have sample line graphs where this is a little bit different information, but we have unemployment rate versus unemployment rates among people ages 25 and older by education level. So you'll notice that the unemployment rate is much higher for students that don't even graduate high school, and the unemployment rate is much lower for people that actually have a bachelor's degree or higher. So what are some general messages that are revealed by the graphs of the previous two slides? So we saw that first one was basically talking about how men on average make more than women for certain, on average for salaries and for certain degrees. So there are three key points to kind of point out here. First of all, greater education does usually mean significantly higher median incomes. The more education you have, typically, not always, but typically means that you tend to get a higher income out of it. For equivalent levels of education, it seems that women earn less than men, and how they gather that data could, I guess, vary. But in this particular graph, it's showing that women earn less than men for equivalent levels of education. It doesn't say equivalent jobs, just says for equivalent levels of education. And no matter what, though, I mean, I think we all can agree that typically the more educated you are, the less likely you'll be unemployed. The more educated you are, you're more likely going to find employment, find a job. So those are two examples, one of a multiple bar graph and another one of a line graph, multiple line graph. We also have something called a stack plot, where you actually can go ahead and stack information on top of each other. Here's an example of a stack plot with using a bar graph method. And again, look at the legend down below here. It kind of just basically shows the average estimated undergraduate budgets. So if you're at a private, that's obviously the most expensive, okay? And you have all the other different values that are going to be added on top of what you actually owe. Notice how each little piece is going to be its own value. So it's $29,056 for nonprofit tuition, private nonprofit, and then it's $10,000 and some change for your living, like your room and board. And then here it's $1,244 for other expenses, $957 for books, supplies, and here $1,570 for transportation, adding it all up to $43,289, which kind of lines up with the numbers here on the bottom. So notice again down here at the bottom we have like 40,000, 45,000, and this all adds up to 43,000-ish. So that kind of makes sense. This is known as a stack plot. Here's a stack plot, but using line graphs. So now for stack plots, though, we have different thicknesses that are going to kind of show us differences between two different, in this case, diseases. Notice here in this particular case that the thickness of this wedge here reaches from here all the way down to here. Okay. It tells you what the wedge is at this particular point in time. So in 1980, we go from 620 down to 180. And we're talking about the difference between people with cardiovascular disease versus people who have cancer. And the question we have down here is, what was the death rate for cardiovascular disease in 1980? So the death rate for cardiovascular disease in 1980 is actually going to be, if we read this here, it's actually going to be 440 deaths per 100,000, because you look at how wide the wedge is what we're looking at. Now, if you'll notice, you might wonder, well, how come were more people dying of pneumonia? No, this is just where they happen to stack it. This is just how many deaths in general were per year, per $100,000 people. So there were not 620 deaths per 100,000 for cardiovascular. There were 620 minus this 180 for cardiovascular, giving us 440 deaths per 100,000. So the answer is 440 deaths per 100,000 in 1980. Okay. Now, the downward slope, though, of the top wedge shows that the overall death rate from these four diseases decreased substantially, which is nice. So it went from 800 deaths per 100,000 in 1900, which makes sense because death rates were much higher. Healthcare wasn't as developed. To now, now it's probably even better, but in 2011, according to this data, it went down to 434 per 100,000. And you'll notice that the gradual disappearance of tuberculosis in the wedge shows that this basically disease was once upon a time was a major killer, but now it's nearly wiped out. And I definitely haven't heard of anyone dying of tuberculosis in my lifetime. However, you'll notice that the widening and narrowing of the cardiovascular wedge shows that the death rate for this disease grew in the first few decades, but it's shown to decline in recent years. And finally, cancer has been shown to kind of rise steadily since the beginning of the century and until about the mid-1900s, or 1990s. But then luckily it has been kind of dropping off somewhat since then. Okay, well, not only do we have things like stacked line graphs like this previous graph was, but we also have graphs of geographical data. So in the figure I'm about to show on the next page is going to show data using a map, and essentially talking about what happens in each state. And you'll notice here that in each state, for this particular graph here, it's basically how much energy is being used per person energy use by state. So this is kind of another geographical kind of map. Another one could be a contour map, is also geographical. This one is actually showing us temperature. So obviously the blue colors, the darker blue and the lighter blue there up top is going towards Canada. You'll notice that those temperatures are much higher, or excuse me, much lower. And one could imagine that maybe what's going on here, maybe these are like the Rocky Mountains here, is why these low temperatures are reaching down into the southern part of the United States. It's probably because we have the Rocky Mountains here. And obviously, we live in Southern California, so we have much higher temperatures on average. This is known as a contour map. But going back 2 more slides, what do we notice about the energy used per person for 2 slides ago? Well, you'll notice that the color coding kind of shows a lot of things, but it kind of shows that if you're in a warm weather state or a more densely populated state, then we're actually using a lot less energy. Because obviously in warm weather states, we're not needing to crank up the heater, we're not needing to use those resources as much. Now, obviously in the summer, we might use the AC more, but also in more densely populations, you're not using as much energy per person. And one of the reasons why we say this is because typically if you want to heat up, let's say, a building, well, that's going to be much more densely populated. So obviously to heat up a building, it's going to take less energy overall per person than, let's say, trying to heat up a whole house if you live like in, say, the Midwest somewhere. That one person heating up the whole house is going to take more energy than several people trying to heat up one building because they're packed in tightly. Also, let's go ahead and take a look. Were there any temperatures above 80 degrees Fahrenheit in the United States on the date shown on the contour map? If so, where? Well, we'll take a look here. Now you'll notice that it doesn't actually show any area where you have temperatures above 80 degrees Fahrenheit in the United States at this particular time, except for this little tip right here. It's really hard to see. It's probably really hard to see on the PowerPoint. But if you see, you'll notice that Florida is mostly red. But if you look down here at the tip here, it is like a darker color red, which means it is, by the way, that says 80 right there. That means everything within that darker red region, the temperatures were either at 80 or higher. So the contour map actually shows us that southern Florida definitely had a temperature of higher than 80 degrees. We also have three-dimensional graphs. Now, three-dimensional graphs are harder to produce by hand, which is going to be a good idea for a computer software to sort of like create it for you. But it definitely gives us richer data sets. Like we are going to be able to like take more complicated types of data and create a graph over it, and it's going to help us to take something that's usually very difficult to read to be precise. So it's a very precise way to read very difficult data, and also many times three-dimensional graphics can be used interactively, where you can actually rotate it or view it from different perspectives, which makes things nice as well. And as an example, when we take a look at something like this, here's a nice 3D graph. You'll notice that it has 3 bits of information. Not only does it have the timeline down here with years, okay, but it also has countries over here, and on top of that, we have CO2 emissions. Now, no surprise here that U.S., China, and Russia are the top 3. In fact, China and U.S. and China seem to be the highest, which kind of makes sense, actually. And these would be probably the 5 most populous countries in the world. So having a 3D graph like this can be give you much more richer data and be able to precisely talk about what would otherwise be difficult to talk about. So based on this figure here, about when did China surpass Russia in total carbon dioxide emissions? Well, we're looking at China and Russia first of all, so let me go ahead and highlight that. We're not talking about any other country, just China and Russia. So this little row in the back here, these red prisms here, these red bars, you can ignore those. We're looking at the blue bars, these light blue bars, and these yellow bars. So based on the figure, when did China surpass Russia in total carbon dioxide emissions? Well, notice here in 1990, Russia was higher in carbon dioxide emissions than China. But then 5 years later, it looks like China surpassed. Now, this specifically says about when. Well, this tells us that China surpassed Russia, maybe not in 1990 and definitely not in 1995, but somewhere in between. So, I mean, I could, I guess, but I'm fine with you guys just stating the fact that China surpassed Russia in total emissions sometime between 1990 and 1995. Now, all this is all well and good, but there's a few cautions I'd like to make. And the few cautions I'd like to make is that sometimes this data looks impressive, looks nice, and you might see something like this and think, oh, that's a very professionally made three-dimensional graph, or there's a very professionally made two-dimensional graphic that you see a stacked line graph, a stacked bar graph, whatever it might be. But there are some precautions you might want to take about reading graphics. Sometimes people can be quite deceptive, especially if they're trying to convince you of something. They'll go ahead and try to convince you using deceptive manners. For example, something called perceptual distortions. Like, so many graphics are drawn in a way that distorts our perception of them. So what if there was like some sort of political poll where they're trying to get you to vote a certain way? Well, if they actually go ahead and distort the perception of the graph itself, they might lead you to believe that there's some data that is not quite there. They might actually cause you to potentially think that data is going to be not exactly what it should be. So be careful with that. And I'll show you an example in a moment. Watch the scale. Sometimes visually deceptive scales could occur. If you're not watching the scales carefully, they might think, they might jump numbers. They might go by 10s or 20s or 30s or even hundreds. If you're not watching the scales, which I'll show you an example in a moment, that could also cause you to be visually deceived and causing you to think one way or the other. Percentage change graphs show that graphs that percentages can also be misleading unless you are very careful about how you interpret those percentages. And finally, pictographs. Pictographs can be very deceptive as well, especially when they are embellishing with additional artwork. Sometimes artwork is going to make you think, oh, this is such a great and wonderful thing, such a pretty picture here, but actually could distract you from the truth. That could be quite dark or quite negative. So some examples, so again, be careful. So imagine, I showed you this graphic in the newspaper. You're going to think in your mind, oh, hey, how much is a dollar worth, right? Well, in 1980, a dollar was worth $1, let's say. Okay. Well, that's, and maybe you might think to yourself, well, that means the dollar was strongest in 1980. Okay. However, if you actually look at the area, it could be deceptive because you might think to yourself, oh, well, that means the dollar was worth more in 1980 than it was in 2005 just because the picture's bigger. That's one. Secondly, this doesn't give us any more information. What this could potentially mean is how much the dollar's worth in other countries, which I guess in some ways that would make this an accurate graphic. But it would be inaccurate if they were saying, let's say, how much the dollar was, how powerful the dollar was in other countries. So, for example, what if for every 42 cents in 2005 was worth $1 in other countries? Well, that means these graphics should be opposite. That means the dollar down here should be bigger in size. So I can kind of show you how this is a slightly perceptual distortion of a potential situation. And again, there's not enough information here too, so who knows what this is trying to convey. Also take a look here. Notice that I have different vertical scales. Notice that the years are the same. Now it says women as a percentage of all college students. You might think, like, oh wow, like, you know, women are really, you know, really killing it over here. Like they were kind of dropping way down and then they skyrocketed, right? But the reality is that if you'll notice that in this graph here, it's a little bit more flatlined, right? Because again, notice the scaling here. The scaling is, you'll notice on the right side, the percentage is a little more spread out. So to me, this is probably a little more accurate view of what percentage of all women, of all college students are women. Whereas this is a little bit more distorted view because this makes you think, oh man, it's so volatile how women, you know, are all of a sudden like, you know, a large proportion of the college population, and then all of a sudden they drop down to a super low proportion of the college population. When in reality, if you were to spread it out and also use a more fair vertical scale, it's actually not so bad, even when they dipped here at the lowest point. Finally, different horizontal scales. According to this actually is showing us the world, the world population in billions of people, and it's projecting kind of like this upward increase. Okay, and if population was that linear, then we wouldn't be so alarmed. It's like, okay, that's not too bad. But if you go ahead and take a look at the years here, the difference between 1 billion to 2 billion, that's over 100 years difference, right? You see that? It's over 100 years to get from 1 billion to 2 billion. But if you jump over here, if you go from, let's say, 7 billion to 8 billion, notice the difference in years there. So this horizontal scale are not the same. So over here, from 1 to 2 billion, I have about 120 years. From 7 billion to 8 billion, we have like, 15 years. So to jump from 1 billion to 2 billion was like doubling the population. It took a long time. But to increase 1 billion nowadays is not that big of a deal. Like we're going to be at 8 billion before we know it. In fact, I think we'll be at 8 billion before 2028, personally. So you got to be careful with how different horizontal scales can deceive. This here seems like the scale is going up, linearly, like in a linear fashion, very straight. When in actuality, population is doing something like this. It grows steadily, then all of a sudden just skyrockets exponentially. That would be a more accurate view of how world population is.